So, you want to learn about particles and all the things that make up matter? Well, you came to the right place because this video is about to explain it. First of all, we gotta learn the very basics. That way we can lay a foundation and eventually get up to the harder stuff like equations and wavelengths and all that. You need to have some background knowledge about protons, neutrons, and electrons. If you don't already know, you can piece together some information by watching this video. So, to understand all the particles, there's a thing that we can use called the Standard Model. What is it? The Standard Model of particle physics is a theory concerning the electromagnetic, weak, and strong nuclear interactions, as well as classifying all the subatomic particles known to man. Here is an illustration of the Standard Model. It contains 3 categories: quarks, leptons, and gauge bosons, as well as the Higgs boson. The quarks category has 6 members: the up quark, charm quark, top quark, down quark, strange quark, and bottom quark, each with a different charge. The up, charm, and top quark all have a charge of 2/3, while the down, strange, and bottom quark all have a charge of -1/3. Each quark has a different amount of mass. Quarks make up all other particles that have mass. The next category on this illustration is leptons. They include the electron, the muon, and the tau, with their respective neutrinos. Next we have the bosons. These include the gluon, the photon, the Z boson, and the W boson. And finally, the Higgs boson. It doesn't act like the other bosons, and scientists think it has the properties that give other particles their mass. Quarks are building block particles, meaning that they can be stacked on one another to create a new particle, while leptons, they like being alone and don't usually interact with any other particle. For example of creating a new particle, if you combine 2 up quarks and 1 down quark, you got a proton. If you combine 2 down quarks and an up quark, you got a neutron. Simple as that. There are 4 forces that help these particles become something bigger, like a proton or neutron. These forces help them coalesce into bigger particles called Hadron, which is the next step up from quarks, leptons, and fermions. Notice how there isn't any correlation of quarks that create the electron. The electron is a lepton, so therefore it's a simplistic particle, but it cannot stack up to make another particle. The quarks use a special kind of force to bind all of them. This force is called the strong nuclear force. The strong nuclear force is also responsible for holding protons and neutrons together. As you can see in this animation, there are 2 clusters of particles. These clusters are the proton and the neutron. Each is made up of 3 particles, one containing 2 downs and 1 up, one containing 2 ups and 1 down. There's a special boson going through them called a gluon. This gluon binds all 3 of them together through a thing called color charge. Gluons travel between the proton and the neutron, causing each of the quarks in the 2 to change the color charge, which then binds the 2 particles together. Gluons travel between the proton and the neutron, causing each of the quarks in the 2 to change the color charge, which then binds the 2 particles together. This is what causes nucleuses of atoms to have neutrons and protons. Even though protons and neutrons are not electromagnetically attracted to each other in any way possible, since the neutron has a 0 charge and the proton has a charge of 1. The neutron is also not attracted to the electron. Since the electron is a lepton, therefore no quarks can be shared. Sometimes, though, this balance between neutrons and protons can get very unstable because of something called radioactive decay. Radioactive decay is caused by another force called the weak nuclear force. This force is responsible for all beta particles, gamma rays, and alpha particles that are emitted throughout the nucleus. Basically what the weak nuclear force does is it forces a proton or neutron to emit a W- boson. It can be positively charged or negatively charged, depending on what cluster of particles is emitting it. This W boson then splits up into one neutrino and one negatively charged particle. This is called beta radiation. Beta radiation happens when the nucleus of an atom is unstable and therefore must get rid of some charge in order to stabilize itself. Radioactive elements like uranium, thorium, plutonium all do this constantly. They also emit gamma rays and alpha rays. Alpha decay is much more efficient at stabilizing nuclei. Alpha decay consists of 2 protons and 2 neutrons, about identical to a helium atom being ejected from the nuclei. This in turn makes the nuclei much smaller in the atomic mass, and it decays a lot quicker. Gamma rays are pure energy. They consist of photons that are being ejected from the core. This happens in fission and fusion. The weak force helps balance all atoms and particles, as well as helping us balance out some man-made particles as well, like plutonium and everything above that. The next one of the 4 forces on our list is electromagnetism. You all are probably familiar with it as you experience it with almost everything in your daily lives. It pulls things together through a magical force called magnetism. Electromagnetism is transmitted through a boson called the photon. The photon travels from one particle to another and basically tells the second particle that this particle exists and what charge it has. Then the second particle compares its charge to that charge, and if they're opposites, then they attract each other and fall into an orbit-like state. As demonstrated in this animation, this electron goes around this proton because of electromagnetism. The electron is attracted to the proton because they have opposite charge. The proton is attracted to the electron because they have opposite charge again. There can be multiple electrons orbiting one proton, and since the electron has the same charge as other electrons, they repel each other, causing them to be locked in a loop, but they don't get any closer to each other or farther away. Because some electrons fall into a specific place around the proton, eventually it's going to get too crowded. That is when the electrons decide to make another outer layer that they can all coalesce in. This makes more space and calls for more massive atoms. An example of this is like iron. Iron has 4 rings, the innermost containing 2 electrons, the second innermost containing 8 electrons, the second outermost containing 14 electrons, and the outermost layer containing 2. As you would imagine, sometimes this can get hectic. As an example, let's take uranium atom, which has 92 electrons and 92 protons. It has 7 rings, each with a different number of electrons on it. As you can see, this is quite a mess. Now, of course, this is on the smaller scale. On a bigger scale, if you have 2 magnets, they'll attract each other still. It's over a much greater distance. The next force on our list is gravity. Its range is unlimited and can reach as far out as it wants. Gravity is sort of special since it acts a little differently than all the other forces. It depends on something, and what it depends on is how much mass the object has. If that object has a lot of mass, then it has a lot of pull against other objects. If it doesn't have a lot of mass, it doesn't have a lot of pull against other objects. Gravity is also pretty weak compared to other forces, and cannot pull 2 atoms close enough together to fusionate them naturally. People on Earth experience gravity every day. It's what holds our feet to the floor. According to Einstein's theory of general relativity, gravity is caused not by a boson or anything like that, but actually the consequences of curvature in space. Therefore, making gravity have lots of weird side effects besides pulling objects closer to the source. In a gravity field, time moves a lot slower than it would have without a gravity field. Since a source of gravity bends space-time that also bends time along with it and space, causing weird distortions with light particles and weird time distortions also. In this animation, there is Earth and the Moon. The Moon orbits Earth because the Earth pulls on the Moon. Although the Moon orbits the Earth, the Moon also has a pull on the Earth, shifting it very slightly towards the Moon. This is what causes tides. Every particle that has mass will have some sort of gravity. Therefore, quarks have gravity, and protons and neutrons have gravity. It is very minuscule, but once you get enough of them in one area, you can get some serious pull. Because of this, scientists believe there is a certain boundary that you cannot cross when you're digging under the Earth. Since once you cross this boundary, the gravity that's pulling up on you because there's so much stuff above you, and the gravity that's pulling down on you, since there's so much stuff below you, is equal, and you would just float in midair. On the surface, we feel the full weight of every single last proton, neutron, and electron pulling us down. Although underground, they experience just slight differences than people on the surface. Gravity grabs a hold of everything, even pure energy, like the photon. If a light particle passes by the sun will have a small effect on the particle and cause it to bend. Scientists know about this, and they use the sun and Earth's positions to accurately predict where the stars are in our sky. Because at certain periods of the year, if you look at one star, it'll be shifted just a little bit, since the sun bends the light just a bit. This effect is called gravitational lensing. It can be better described by a black hole, since a black hole has a lot of gravity and can easily bend light. Gravitational lensing also has another special effect on the way you see things. If light somehow passes through a massive gravitational field, it won't just bend and change direction. It'll also bend the actual wavelength and make it most likely longer. The wave will then stretch, becoming more red and red, until finally it just disappears into black.